This is a video for AQA Further Pure Mathematics. This is Matrices 2.2 Rotations in 2 dimensions. Firstly, I'd like to look at the transformation given by this particular matrix by considering its effect on a triangle ABC. So this triangle here, ABC. Well, we can consider the triangle by looking at its matrix, which is written down there. A is 1, 2, B 5, 2, and C 5, 4. Then if we do the product of those two matrices, we can see that it's actually quite straightforward. When we look at the top line, the 0, -1, that's going to produce negative of the bottom line along the top here for our image matrix, so -2, -2, and -4. Then if we consider the bottom line, the 1, 0, that's just going to produce the top 1, 5, 5 at the bottom of our image matrix. So A dashed, B dashed, C dashed, the 3 points are given by this new matrix. Now we can see therefore that we've got a rotation here which is 90 degrees about the origin. It's a rotation anti-clockwise, which we'd usually write as being plus 90 degrees. So in rotations, the positive direction for a rotation is anti-clockwise. We can find the matrix for a transformation by considering the left-hand rule. Remember that in the left-hand rule, the thumb represents the unit vector I, and the index vector is the index finger is given the vector j. If we then consider what happens to these in the transformation, so this is going to be a rotation of 90 degrees in a positive anti-clockwise direction, then we can see then that I has become 0, 1. So this is I dashed is 0, 1, and j has transformed onto -1, 0. So j dashed is -1, 0. And these then produce the two columns of our matrix. So the rotation matrix 0, 1, -1, 0, 90-degree rotation. So the first column is the thumb, the second column is the index finger. So we're looking at the vectors 1, 0 and 0, 1. Now sometimes to do this you have to be a little bit of a contortionist. So rather than actually using your hand, it's actually quite straightforward just to consider what happens to the vectors by drawing a little diagram. This is I and this is j, and if we do a rotation of 90 degrees, then they will end up with I pointing upwards. So I dashed is there and j dashed is there. So I dashed 1, 0, j dashed -1, 0. So a quick diagram produces the result a little bit more easily perhaps than using your hand and getting in a twist. I now want to consider a slightly more complex situation, this time an anti-clockwise rotation of 135 degrees about the origin. Well, we can do exactly the same as we've done before, considering the vectors I and j and seeing where they end up when we do the rotation. So this is a positive 135 degree rotation and we end up in this position. Now what we need to do then to calculate the matrix is to calculate the value of I dashed, which is this vector here, and j dashed, which is this one. Now remembering that the vectors themselves are 1 unit long, then we can calculate the x and the y values of the vectors by considering this angle here, which will be 45 degrees. So for I dashed, the x value, or the length of that line there, will be sine 45, which is root 2 over 2. And the height, the y value, will be here also, this time cosine 45 degrees, which is equal to root 2 over 2 as well. Likewise, we can consider this angle here as 45 degrees and calculate the opposite side and the adjacent sides for this triangle, again with values root 2 over 2 and root 2 over 2. Now remembering that some of these are negative values, so if we look at I dashed, we can see that it has a negative x value, so negative root 2 over 2, and a positive y value, so root 2 over 2 there, and j dashed, again, this time again a negative x, so negative root 2 over 2 and negative root 2 over 2. Now there is a general matrix for rotation by an angle of theta, which is given by cosine theta and sine theta for the I dashed, and then negative sine theta and cosine theta for j dashed. And if you use that here with theta equal to 135 degrees, then indeed you will get these values. So then it's going to take care of the negative signs, because sine of 45 degrees that we used in the example is equal to negative sine of cosine 135 degrees. The rotations that you need to be familiar with then are given by the following matrices. First one, there's a rotation of 90 degrees about the origin. That's anti-clockwise, so it's the plus 90 degrees. The second one is a rotation by negative 90 degrees or clockwise about the origin. And third one, 180 degrees. And finally the general one, which is a rotation by an angle theta, where theta can be positive or negative, and you can use that for those other angles, 135 degrees, etc., that you might be asked to do. Notice in all of these, a clockwise rotation is negative, anti-clockwise is positive. You can do a little bit more investigating about the unit vectors and how they're used by looking at a GeoGebra file, which is using the tiny link that's there. Well, that's the end of section 2.2. In the next video we'll look at 2.3, which considers stretches, enlargements